This is Statistics for Data Science, and this is the second lecture, Probability Spaces. This afternoon we will have the first real Übungssession. Before I start with the lecture, are there any questions regarding the lecture? Not the Übung. Übung questions we can deal with later, but is there anything that you would like to discuss regarding the lecture before we start? If so, just make yourself known. Good, so you can hear me, there are no questions, so we can start. So the topic today are probability spaces, and that's a very foundational topic in probability theory. So for all of you from a mathematical background, and for all of you who took mathematical probability theory courses, I hope there's not too much new stuff in this lecture. That's also a little bit of the idea, so that you refresh what you have learned, and then my personal experience with these kind of things is that it's helpful to be able to learn them multiple times. I kind of re-study them every year when I come to it, because they are abstract and they need some time to sink in. So that's fine. If it's all new to you, then see it as a first exposure to abstract probability theory. So this, as I mentioned last week, the first 6 or 7 or so lectures are related to probability theory, of course with a focus on things that are interesting to statistics, for example random variables, probability distributions, and random variable transformations, and so on, and expectations. So on, all of these things have very immediate consequences for statistics. Maybe the least statistical lecture is actually today's lecture, because often the probability space model sits there in the background in statistical models, but it's not made explicit. But then of course it's good to know that it's there in the background. So the material that I present is fairly standard. These are some references. So Wassermann, chapter 1, discusses this. Casella and Berger discuss this. There is a section on this, of course, also in De Groot, which I didn't include here because it's a little bit less less in spirit than what we do here, although the remainder of these probability theory lectures will mainly feature De Groot, but there they are a little bit not weaker, but less explicit maybe. And then there are of course very good references on probability theory with not statistics in mind, and these are these books by Billingsley, Friestedt, Rosenthal, if you're new to if you want measure theoretic approach to probability theory. So these are all very good references, but it's very standard material, so there's nothing special here. You find introductions to probability spaces essentially in all probability theory books, and in good statistics books you find them. You even find them in certain books for statistics for psychology, for example, where you wouldn't expect them to find, and they are not well integrated, but they are there, so it's really standard material. So the plan is today then first discuss the abstract probability space model, then introduce some, or revise or rehearse or refresh some very basic aspects of probabilities, and that's then basically everything that we need to go on next week and the weeks after when dealing with random variables, which are the core constructs that we are actually concerned with in statistics. And to exemplify some of the probability space theory, we will have exercises later on. And so let's start with probability spaces. And I'm jumping right in here with the abstract definition of a probability space. This will also be kind of the style a little bit of this lecture, so it's kind of a math teaching inspired approach. So instead of coming up with examples and then deducing some abstract thing in the end, which is kind of a physics approach. I always feel we will start with definitions and then have things there and are able to deal with it, and then we hopefully, if the definition is not completely transparent, comment a little bit on it and look at examples so that it becomes clear what the definition wants to say, and also maybe even how the definition is motivated or why these abstract ideas. So the most important thing about a probability space is to appreciate that this is a fairly abstract model of random experiments. Abstract meaning that you can adapt it, it's fairly versatile and you can adapt it to many specific cases. So what's the definition? A probability space is a triple, so just this little thing with 3 ingredients, namely omega, calligraphic A, and P, where omega is a set of elementary outcomes, small omega. R is a sigma algebra, and a sigma algebra is a specific set in set theory, namely a set with the following properties. Omega is in A, this is why it's also usually referred to as a sigma algebra on omega, so the sigma algebra is with respect to big omega. So omega itself is in the sigma algebra. The sigma algebra R is closed under the formation of complements. So if A is in the sigma algebra calligraphic A, then also the complement of A, and the complement here and always is defined as omega without A. I think I read this week that this is called there are 2 forms of complements I recently figured. For me, this was always the complement. So it's either with respect to a superset, and this is what is meant here. So if this A is in the sigma algebra, then also the complement, this is all the elements in omega which are not in A, is in the sigma algebra. So for each set that is in the sigma algebra, the complement of this set with respect to the superset omega is also in the sigma algebra, and the sigma algebra is closed under countable unions. That is, if you have a family, or if you want a sequence of sets A1, A2, which are countable, so which can bijectively be mapped onto the natural numbers that are in the sigma algebra, then also the union of these sets is in the sigma algebra. So this is just the definition of a sigma algebra, these points. So it would actually be enough if everybody knew what a sigma algebra is to just say omega is a set of elementary outcomes omega and R is a sigma algebra. Done. These things are just the definition of the sigma algebra put here into the definition of the probability space to make it more explicit. So we have a outcome set omega, we have a sigma algebra, and then we have a mapping P, which is defined on the sigma algebra, so it takes as input sets, because the sigma algebra is a set of sets, and maps them onto the interval from 0 to 1 with the following properties. The values that this mapping takes on for all sets in the sigma algebra are non-negative, so larger or equal to 0. The value associated to the full omega set equals 1. And finally, P, this mapping, which we will later call also, which of course you know that is a probability measure, has the probability of sigma additivity, which means that if an possibly infinite sequence of A1, A2 in the sets in the sigma algebra are pairwise disjoint, so they have no, they don't share any elements, then the value that P assigns to the infinite union of these AI corresponds to the infinite sum or the series of the values that P assigns to each AI individually. And of course, this holds also for finite parts, finite sequences of sets. So that's the full beauty of the abstract probability space definition. And of course, if you think about probability and things like random events and games of chance, or measuring data and modeling this probabilistically, on first sight, this of course has little to do with that. So because these are abstract things, it's mainly so from a mathematical perspective, it's set theory. So we have this definition of a sigma algebra, which is fairly set theoretic, and then we have a function which has specific properties. So there is no immediate connection to intuitions about probability in there. But of course, this is just the abstract way to describe this model. And now on the next slide, I try to elucidate a little bit what this now has to do with probability. But before I do so, I point out that this goes back to Kolmogorov. So that's this Grundbegriffe der Wahrscheinlichkeitsrechnung from the 1930s. And like he says in the introduction, the purpose of this monograph is to give an axiomatic foundation for the theory of probability. This is also, of course, in the history of mathematics, that's always the case. First, people start to calculate and do things like they do these days in, I don't know, neural networks or something, and then later on people start to think about what actually is being done, and it's tried to kind of ground all of this. And so this was the purpose also here. The author himself said the task of putting in the natural place among the general notions of modern mathematics. And by modern mathematics, what Kolmogorov has in mind is set theory, according to Cantor, mappings, and Lebesgue integrals. So the Lebesgue integral notion was only developed around in the early 20th century. The basic concepts of probability theory, concepts which until recently were considered to be quite peculiar. So what this great contribution is there is that these intuitive ideas about how probability theory can be used to model, or these intuitive ideas about probability theory, about probability can be formalized. And what the point of this monograph and also this probability space model is that there is a very close connection of set theory and mappings to probabilistic intuitive models. And I highly actually recommend to have a read of this book. When I first had a look at it, I was surprised how clear it is. So for example, there is a clear not a one-to-one, maybe it's a one-to-one mapping, but there's a mapping between the set theoretic ideas and how they relate to ideas about random events. So it's fairly explicit on that, and tries to really show that these abstract set theoretic notions map nicely onto the intuitive ideas about probability. So it's not a very abstract and dense or something book. It's really kind of in a way very didactic. So I recommend having a read of it. Now, what is it with these probability spaces, and what's going on there? So I called the slide selected remarks. So these are some remarks that one can make about probability spaces. Of course, one can do a lot more. So first of all, probability spaces are used as abstract models of random experiments. So this is kind of like I pointed out last week, in statistics and in data science and in data analysis, you always have a model, and in a way I wouldn't say the most abstract model, but a fairly abstract model if you buy into the idea that you want to quantify uncertainty, is this model of probability spaces. So we are dealing here with a model, right? So it's a model It's not the real world, it's a model of the world that has been developed by humans. And it's a model for random experiments. So random experiments in a way meaning kind of the real world in this case, where humans think that there is some randomness involved. And the trick then is of course always to do two things with models. One thing is to understand the mathematics of the model, so the inner workings of the model and the logic that other people have built in there and have developed, and to really become clear about the inner logic of the model. So that's one thing that's always important when understanding models. And the other question is to see how this can now be used to model real-world phenomena, but then always, of course, always as a model, right? So it can always be not quite correct, and modeling in the end is an art. So there are also no strict rules. I mean, there are more sensible things and less sensible things, as we will actually see here in probability spaces when we apply it to an example. But there are no clear-cut rules. I mean, that's in a way different from the inner workings of the model. So in the inner workings of the model, there are laws and there's logic, and people can say this theorem doesn't follow from these axioms. You made a mistake there. That's clear. But if you apply this model to real-world phenomena, you can do more sensible and less sensible things, I think, but you cannot really be wrong. Unless you didn't really understand the inner workings of the model, then it's likely that you make something weird. So probability spaces are special cases of measure spaces. Measure space I denote here with omega r mu, where mu is a measure, not necessarily a probability measure. And of course, measure spaces are mathematical models for assigning volume to sets. So this then relates probability theory and this measure theoretic approach to probability theory to measure theory proper, and measuring volumes. And this was, of course, one of the contributions of Kolmogorov, that this measuring volumes in the Lebesgue integral sense can be nicely mapped to assigning probabilities to sets. The question is, where then does some notion of randomness come in? And a very important aspect here is that will also play a major role when we later talk about random variables, is that the elementary outcomes can be conceived as being realized according to the probability measure that is assigned to them. So if you look at all the elementary outcomes, small omega in a probability space, and you look at how much volume they get assigned to, so how much probability measure they get assigned to, then you can always think of, well, if you put them on a I don't know, if you put them on a table and then select uniformly from this table at a given location, and you have the table kind of partitioned into the different volumes assigned to a given elementary outcome. If you then pick uniformly on your table, then of course the probability that you find a specific elementary outcome is a function of the volume that is assigned to it. So this is kind of the sampling, and this idea of randomness comes in as realizations of the elementary outcomes, which are realized according as to how much probability measure they get assigned to. Now, from a mathematical perspective, the real power of probability spaces, in my opinion, comes from the fact that they unify finite, countable, and uncountable outcome sets. So finite outcome sets, so think of the dice experiment, or coin tosses, or roulette, or whatever, are kind of readily approach, and you have probability mass functions as we will here, and that's relatively straightforward. But then of course the real numbers had been developed until 1933, and dealing with these uncountable outcome sets from a mathematical perspective, that was not trivial. And with the probability space model, you have a model that has a language that then can apply both in the finite, countable, and an uncountable case, and that's really powerful. So if you want to make statements on in general about how certain things work. So for example, I worked on variational inference, and the question was, how does it work? How does it look for finite, and how does it look for finite cases, and how does it look for real numbers? Then it's of course very useful if you have a language that unifies both, and this is what they offer. And this is when you really see the power. I think before you have a problem like this, it's more like, yeah, there's this abstract model, and but you don't see really how it can unify discrete or you don't see the real power. But let me tell you, the probability spaces of a language spanning discrete and continuous probability. We will, and this is also, if you look at mathematical statistics, of course, in the end you have often you have a concrete model where you have discrete or random variables, or maybe a mixture of both, but you deal then with a model that is either continuous, discrete, or both, but you don't need to make statements about all possibilities that can happen. So that's when you then again don't see this power and don't need to deal with it. But on the other hand, it's good to know that everything is grounded and there's a logical basis for that. Now, the sigma algebras, what's their role? They, of course, play the role of complete sets of events, and each event comprises the elementary, or comprises a specific set of elementary outcomes. So the sigma algebra basically allows to have a model of everything that can happen and everything that you might want to assign a probability to. And for the sigma algebras, we will see in examples that for finite outcome spaces, the typical sigma algebra is the power set. So the power set just being the set of all subsets, and that is everything that you might want to assign a probability to. For real outcome spaces, so for the real numbers, the Borel sigma algebra fulfills the same function, and this is actually where something that we don't pursue here. So the construction of the Borel sigma algebra and how it relates to the power set. So I know that the Borel sigma algebra is not corresponding to the power set of the real numbers. It's actually smaller, but that it doesn't hurt to think of the Borel sigma algebra as the power set of the real numbers, because then one has a clear intuition and one also knows what the role is. So the sigma algebra basically playing the model component of being able to formalize all possible events. And then finally, the actually probabilistic characteristics, they are of course defined by P, the probability measure, and of course they define on the specific characteristics of a given probability space model. As I already mentioned, and we will see, probability spaces often disappear behind random variables and distributions. We will make this very explicit when we talk about random variables and distributions in the next lecture. In the end, when dealing with probabilistic models, of course you don't, in formulating a probabilistic model, for example, for a continuous random variable in terms of a probability density function, or a continuous random vector and its probability density function, you don't always have to write down the probability space model, and it would also just be overkill. But if you then kind of have more general questions and try to go from your specific model to general classes of probabilistic models, and maybe even try to bridge discrete and continuous random variables, then you can always invent or make an explicit the probability space behind your specific probabilistic models. And then of course, probability spaces, if you study certain things like random fields, Markov kernels, or things like that, then you will often find that probability spaces feature there prominently, and these kind of things like random fields or Markov kernels are in their definition are used sensibly and usually defined based on probability spaces. So it also makes sense to know about probability spaces just for the pure reason to be able to understand definitions of other concepts that may or may not be of more interest. Good. So that's kind of a little bit of a discussion. So let's make this now explicit with an example. So the example is, of course, the typical example that you always encounter first, throwing a dice. And what it means to formulate a probability space model of something, a real-world phenomenon, a random experiment, is just to define what omega is, what the sigma algebra R is, and what the probability measure P is. That's basically applying this model to a real-world scenario. And now we think of throwing a dice, so this cube little thing that you can in games of chance throw, and then either one then pips come up. These little dots on dice are called pips, and you know that it's that typical dice are six-sided. Of course, you can have other dice, but the typical one is six-sided. So the elementary outcome set then could be, for example, the natural numbers 1, 2, 3, 4, 5, 6. Because these are the elementary outcomes that can be realized in a die or in a dice. However, there is nothing that necessarily says that the outcome set needs to be numbers. So as another example, I here try to visualize pips, so 1, 2, 3, 4, 5, and 6. And you could also use these as elements of your outcome set. And then if you want to calculate with that, of course, you would need to map them using a random variable onto some numbers, but only if you really wanted to calculate with them. For this is of course a finite outcome space, so there's a finite number of values in the outcome space, namely 6, or elements in the outcome space. For these kind of cases, the power set of the outcome set is a reasonable sigma algebra. Of course, in probability theory, you prove that the power set is always a sigma algebra. We don't do that. We just state that power sets are sigma algebras. And now, what's the role? So we have the set of all subsets, and I selected certain subsets here. So I selected the full set, selected the subset with the elements 5 and 6, so going from this outcome space, the subset of only 2, 4, and 6, the subset of 6, and the subset of 1, 3, and 6, and the empty set. Now, these subsets, they can be, of course, interpreted or stated in normal language, and then it is immediately clear what this event notion is. So for example, if you think about the subset 5 and 6 of omega, then 5 and 6 are of course numbers larger than 4, and if you now are in the dice scenario and you wonder what the probability of a number that is the probability for a number larger than 4 to occur is you can ask what is the probability measure associated with the subset 5 and 6. And the same, for example, for this 2, 4, and 6. 2, 4, and 6 are of course even numbers in the outcome set. So if you are interested in the event an even number occurs, then you can use 2, 4, and 6. Of course, usually you would go the other way around. You will not start with being interested in subsets of the elementary outcome space, but you will be interested in a specific event. For example, an odd number occurs. So what's the probability that an odd number occurs? Or what's the probability that a number larger than 3 occurs? Then, of course, you need to think of what's the corresponding subset of the elementary outcome space. So, for example, for an odd number, that would be 1, 3, 5, which is not listed here. But whatever you think of, you will find a corresponding set in the sigma algebra, because it's the set of all subsets, so there is nothing more. And yeah, in a way to make this also explicit, there's this event 1, 3, or 6 occurs, which is kind of a weird event. It's not something that you would immediately, for example, bet on. But then, of course, 1, 3, or 6 is also just a subset of the elementary outcome set, and it's, of course, in the power set. And then there's also the event that no number occurs, which is the empty set. And the empty set, as we will see, of course, always gets allocated probability of 0, so this cannot happen. However, this is again where you see that it's a model. Of course, it can happen that no number occurs. For example, if you throw the dice and it falls off the table and it goes under the couch, and then you don't see a number and maybe can't recover the dice. So it's this probability space model is of course a model. Of course, it can be that no number occurs. Maybe even if the, I don't know, the dice breaks or something like that. But the model says that the probability of this is 0, and in real life, I mean, if you play, for example, with kids and they throw the dice really hard, or somebody's losing and then throws the dice out of the window or something, this can happen. So after all, this is just a model of throwing a dice. And if you want to account for the fact that you have kids that don't like to lose and throw the throw the dice out of the window, then you might want to include an elementary outcome, I don't know, 7, which encodes that dice is destroyed, which then gets a positive probability. What we will take as a given and also not prove is that P can be defined by specification of the probability assigned to the elementary outcome sets, because then we can always for each set compute the probability of this set or event by means of the sigma additivity of P. There's actually a P missing. There we need a P. Typo. This should be PA equals the sum of omega in a P omega. So if we define the probability associated with each elementary outcome, then for each event we can evaluate the probability by summing over the probability of the elementary outcomes that are in this specific event, or this specific subset of omega, or this element of the sigma algebra, which are all the same thing. Sorry for the typo, but there will be more typos. So if you discover typos, always please send me emails. Then I'm trying to clean them up. Now, of course, how this model works exactly depends on how we define the probabilities associated with elementary outcomes. And typically in a dice that you consider fair, you would say it's 1/6. However, that's just a modeling choice, right? So this is also not something that is built into probability space theory, but that's because you think that it's equally likely that each side comes up. If you have a biased die, biased dice, then you might not do that. So, for example, you could assign to 1, 2, and 6 the probability of 1/9, and Does that so that makes sense? Yeah. And to 3, 4, and 5, the probability of 2 over 9. So that would be 6 over 9 from 3, 4, and 5, and 3 over 9 from 1, 2, and 6. So you have assigned the probability to the entire outcome space, which always needs to be 1, as we've seen before, and this then would be a biased die. So that a die is fair, that's an assumption, or that's inherent in the model. So you model a fair die, but you can also choose to model a biased die. Yeah. So these are all modeling choices, and so again, so you have kind of freedom what you define as the elementary outcome set. You then need to make sure to have a useful model, and not so with the sigma algebra, it's also about being useful. It's not to torture people to understand what a sigma algebra is, but it's there to make sure that you don't end up with a model where you then have, for example, in this case, you're interested in the event an even number occurs, and then you realize, whoa, that's not in my event set. So then you have a fairly useless, or it's not that awesome model. And by using a sigma algebra as an event set, you make sure that this cannot happen, and also by making sure that the probability assigned to omega is always 1. So what I was trying to say is that in omega you have quite a lot of freedom. When choosing the sigma algebra, you don't have that much freedom. You just need to choose a sigma algebra, but it's the model helps you, and by choosing a sigma algebra, you make sure that it's a good model or useful model, let's say. And in choosing P, you then can do different things and see in your model, when kind of, for example, simulating the model either analytically or actually computationally, you can see what happens if you make these assumptions. That's like modeling COVID. If you assume that although many people are not, or nobody is supposed to meet someone else, but you assume that like 10% of the people don't hold on to or don't follow these regulations, what happens then? And this is exactly what you can do here. Let's see. Yeah, that was also already everything I wanted to say about probability spaces. Yeah, I think this would be a good time for questions, because then we can have a brief break afterwards. So are there questions regarding this abstract probability space model? Okay, in the exercise session we will actually see more examples for probability space models. Here, of course, I only focus on one example so far, but we will see other applications in this very basic random experiment case. Okay, then I suggest we have a break and start again at 8:30. To discuss some features of probabilities in these basic probability space models. Good, then let's have a break. Okay, then let's continue. Maybe briefly go back to this. I just put in the P that I said was missing. Now it's there. And having introduced probability spaces, now let's discuss some basic aspects of probabilities. Of course, this is by no means exhaustive or comprehensive. After all, we are not doing a course in probability theory, but in statistics. So I'm just highlighting certain aspects here, and mainly those that we will need in later parts of the lecture. Yeah, so that's not a comprehensive introduction to everything that could be said about probability measures, of course.
Sorry?
Yeah?
Have you heard the question? I think there was a question in advance.
There was a question about what?
I think Michelle asked something.
She asked something and I answered something.
Ah, okay, then we totally missed your answer. Okay, sorry, then it must have been a connection problem.
Okay. Good. But yeah, let's yeah. Let's because I'm also recording all of this. Let's have pre-located times for questions, please, and not at random points, because then it gets really hard to cut out all of these things where other people talk and privacy issues get violated. Okay. Elementary probabilities. So we first look again at the notion of a probability measure. This is the same probability measure, of course, that was also already included in the definition of the probability space. But I wanted to, so what I'm referring to is this here. I'm just stating it again to now focus in on probability measures and not sigma algebras or something. And to this end, I define it here. Maybe that's also not fully consistent with the above. Let omega denote an outcome space and R denote a sigma algebra function from the sigma algebra to the real numbers. Above it says to the interval 0, 1, but it will become clear that this is the same thing here in a second. That allocates to each A in the sigma algebra a probability PA and satisfies the following axioms, namely that the probabilities are non-negative, that the probability of omega equals 1, and that exhibits the sigma additivity property that we already discussed, is called a probability measure or probability. And one can show, one can already at this level show certain equivalences, so that one can either define it like that and then certain other things follow, or one defines it like that and then other things follow, and so on. So one can do little proofs and calculations already at this level of the definition. I'm just trying here to refresh the fact that the probability measures are always numbers larger or equal to 0. The probability for the element for the full outcome set is always 1, so they are normalized, and they exhibit the sigma additivity property. The question is, of course, this is the mathematical definition, what is the intuitive meaning? And there are two kind of main interpretations of that, in a way, if you want, the frequentist and the Bayesian. So on the one hand, you can interpret the probability of an event as the idealized long-run frequency of observing A. This is, of course, based on kind of things like the dice model, where if you want to know what the probability of the elementary outcome 1 pip is, you can of course throw your dice many times and record the outcomes you observe, and then at one point you might find that this is roughly 1/6 if you have a fair die. I should say fair dice, not fair die. And then the idea is that you could go on doing this forever, and then if you compute this long run frequency, for example, of the number of observations p and trials over all trials n, and you let n go to infinity, then this is the probability. I find, yeah, it's fine, but it assumes that there is something real like probability outside in the world, and specifically if you do a die experiment, that you then in the end really would end up at 1/6, but of course that depends on the exact physical properties of your dice and so on. So what I can, from this model-based perspective, identify more, which is that you interpret the probability as some subjective degree of belief that A is true or that A occurs, and that's because there you don't need to start with doing experiment, which then somehow defines something in your model, but then it's not enough to do this experiment, but you need to assume that you have this idealized experiment that runs unto infinity, which no real experiment ever does, because or everyone dies. I rather, of course, from a sampling perspective and from doing computer simulations, this frequency reflection, as we will see also in the exercise, is very intuitive. So if you have 4 elementary outcomes and the probability for one of them is 1/3, then you expect that if you simulate this in 1/3 cases, you observe this. That's fine, but to use this as a definition, so based on some experiment, I don't know. The easier is that you say, okay, this is all just a model. We described uncertainties. We don't know. We assign a belief that this happens in 1/3 of the cases to that, and then we observe, if we sample something, that this happens in 1/3 of the cases, and we say, okay, our belief doesn't seem to be that detached from the reality. I find this much more natural. There is, of course, you can read a lot of things called computational philosophy, or however mathematical philosophy, about the interpretation of philosophy. You can read De Finetti, and I think so. I agree with De Finetti in this idea that probability does not exist, in the sense that there are no probabilities in the world. This is a model. This is how humans make sense of the world, and there is no objective probability out there. In any case, these are more philosophical ideas, and we don't focus on them that much, but we try to understand the technicalities here, because it's nice to have philosophical discussions, but you can have them in the evening, and in the morning you need to understand what's going on and do technical stuff so that you actually know the inner workings of this and can apply them. One important thing is, of course, with respect to frequencies and Bayesian statistics and Bayesian probability, which we will see then also in this course. So in the beginning, starting with a lot of frequentist stuff, and then in the end going to the Bayesian viewpoint, that of course the technical framework, the formal framework, is exactly the same. So it's not that this foundational idea about probability spaces doesn't play a role in the Bayesian world, or that it plays in the probabilities have different properties in frequentists. They are just interpreted differently. But from the calculus and the mathematics, it's exactly the same. And actually, this whole these are just two interpretations, and it's not there's nothing. You might even, if you look into the literature, you might even find more interpretations for probabilities than just the two that I've mentioned. Going back to the technical side, so here are some basic properties of probabilities which follow directly from the definition. And if you look into the books that I recommend, of course, you find proofs for all of them. And these are, of course, little exercises that one can do to see how these things follow from the definition. We will not go over proofs here of these things, because that would just take a lot of time. So recall that the probability of the empty set, so in the DICE experiment, no number occurs is 0, and the probabilities are always bounded below with 0 and above with 1. You might have noticed that this was to the real numbers, and from these definitions then already follows this. In the earlier definition, I put the interval already up there in the definition, but it follows also from this other definition, so it's doesn't really matter. If you have a true subset of some other subset, so if A is a true subset of B, then the probability assigned to A is smaller or equal than the probability assigned to B. The probability of the complement, if A is the probability of A to happen, then the probability of A not to happen is 1 minus the probability of A to happen. If you have non-intersecting sets, so disjoint sets, so if the intersection of A and B is the empty set, then the probability of A and or B is the probability, so of the union of A and B is the probability of A plus the probability of B. And if the sets are not necessarily pairwise disjoint, so there might be some elements in the intersection. Then the probability of the union, so of the event A and or B to happen, is the probability of A plus the probability of B minus the probability of A and B. And for the latter, I have a little proof here on the slide. And of course, one can study all these proofs, and it's interesting, but it also takes some time. So to prove this last here, so that the probability of A and or B, so the union of A and B, can be decomposed in the probability of A plus B minus the probability of A and B. It's first helpful to rewrite the probability of A and or B as the probability of A and A and the complement of B. So here we have, I try to visualize this here with a Venn diagram, where you have the elementary outcome space omega, and then you have two events A and B, so two subsets of omega which are partially overlapping. So you see that there's some overlap, so some elements are both in A and B. You can write this probability first as the probability of A intersecting with the complement of B, which is of course everything in omega which is not B, so that would be this blue thing, because this thing here is also in B, plus and the probability of A and B, so that's this thing where these two sets overlap, and the probability of the complement of A intersecting with B. And these are pairwise disjoint, so you can use the sigma additivity, and of course you can prove formally that they are pairwise disjoint, but you can also see that they're pairwise disjoint based on the Venn diagrams, although of course I know that we mathematicians don't like Venn diagrams. So then you can first rewrite A and or B as the sum. And then what happens in this little proof is that A and B is added and subtracted, so nothing happens. And then they are put together into the probabilities, so based on sigma additivity, so A intersecting with BC and A and B are pairwise disjoint, so we can we can rewrite this sum here as the measure assigned to the union of this. The same goes with this thing here and this, and then we have the union of A and the complement of B, and or the union with A and B. And you might know from elementary set theory that the union of the intersection of a set with the set again with the intersection with the complement, this is just A, so everything that is in A and the complement of B together with everything that is in A and B itself, that's A, so this evaluates to A, this evaluates to B, and then there's 1 minus P and B, and then you get to this formula. So these are these little proofs that one can clarify for oneself, sometimes with the help of Venn diagrams, sometimes by very explicitly writing this out. And yeah, it's helpful if you need a certain equality to check again and to really immerse in that when checking the proofs. But here we really don't want to go more into details of that because we don't need it. What we need, and which will be a fairly important thing most of the time, is independence. And independence we formalize here by the mere fact that the probability of the intersection of A and B is factorizes into the probability of A and the probability of B. This can be kind of generalized to multiple events, and then calling a set of events AI for an arbitrary index sets I as independent if for arbitrary subsets of J the intersection of these arbitrary subsets, the probability of the intersection of these arbitrary subsets of these AI is given by the product of the probabilities of the individually sets in this arbitrary subset. So for example, if you have 3 sets, then for them to be independent, so if you have 3 sets A, B, C, then to say that these sets are independent, A must be independent of B, A must be independent of C, B must be independent of C, and A, B, C must be independent. Then you call them independent if only A is independent of B, A is independent of C, and B is independent of C. You call them pairwise independent. The thing is, what about independence? So there one also needs to kind of, and we will get back to independence many times. Independence can come into a model by via 2 sources. So one is that you want to assign independence of events because you have good reasons to believe that one event doesn't influence the other. So then you build independence in by assumption. So that's a typical thing in kind of more interesting probabilistic models than we are dealing with, so that you build in certain usually then conditional independence properties and have them in the model by design. However, you can also have the fact that, and you have the fact that if you build in certain independence properties into your model, or conditional independence properties, then other independence properties follow. And of course, what intuitively independence tries to or models is the absence of deterministic and stochastic influences. This, I think, gets clearest if we look in a second at the notion of conditional probability and the fact that what happens if independence is assumed. But yeah, one needs to be clear that independence usually enters, and we will see that many times when we talk about statistics, enters by design. So we assume that that certain random variables are independent, and then we study what the model brings. But of course, it's a mathematical modeling choice, and this mathematical modeling choice can be more or less valid. So for example, if you assume you have human participants in an experiment and you assume they are independent, so they if one of them behaves in this way randomly, then the other person that not necessarily follow in this random direction or goes into the opposite direction and so on. This is an assumption, and it may or may not be violated. So for example, if these are participants in an experiment or whatever, and they have talked to each other before, and or maybe are friends or whatever, then this assumption might not be true. But it's an assumption. It's nothing that you can prove. You can only prove independence within a model if you based on certain features of the model that you built in previously. So independence may follow from the design of a probabilistic model. One thing that is interesting, and that we can also look at later on in the exercise, is that if you have disjoint events with positive probability, they are not independent. So if you have positive probability for an event A and B, and for both of them, and you multiply them, then of course you get something larger than 0. But the probability, because they're disjoint for A and B, is of course the probability of the empty set, which is 0. So then this basic definition of independence does not hold. So if you have disjoint events with positive probability, they cannot be independent. And this already was something that I explained. We will see an example for this later on when we look at the DICE experiment. So I think this notion of how independence models the absence of influences, I think that's best understood if one looks at at conditional probability, and of course we will need conditional probabilities mainly later when we talk about Bayesian statistics. In frequentist statistics there's not that much conditional probability. We use this definition of conditional probability if the probability of B is larger than 0, then the conditional probability of the event A in the sigma algebra is given B in the sigma algebra is denoted as A given B. So this vertical, why does this not go away? Anyway, now it's going away. The vertical bar means A given B, and it's just defined as the probability of A and B, so the intersection of A and B divided by the probability of B. And of course you can only divide by the probability of B if B is actually assigned a positive probability, and if this is not the case, then the conditional probability is not defined. For the mathematicians, you might know that you can give more general definitions of conditional probability, I think in terms of Markov kernels, that also account for the fact that you can, or that they're also allowed to define probabilities given zero or null sets, but this is again not of interest here. So we always assume that the probability of the event B is larger than 0. And then it's important to appreciate that for a fixed B, this P A or some other A given B is a probability measure. That means this P dot given B is always larger or equal to 0. The probability of omega given B is 1, and you again have sigma additivity. So again, I think this should be proven, but here the main point is that if we have a fixed B with a conditional probability of one event, we can of course define not only for one event A, but for all events A, and then we have a probability measure over the events in the sigma algebra given B. Yeah, how now to understand this? One way to understand is that the probability of A given B is the fraction of the times that A occurs among those in which B occurs. So let's say B has occurs in 40 of 100 cases, and in these and then A and B occur in all 40 cases. Then of course A always occurs when B occurs, and the probability of A to occur if B occurs, so the conditional probability of A given B is 1, but maybe A and B only happens in, let's say, 20 of these 40 cases in which B occurs, and then the probability of A given B is only 1/2. So that's one way to interpret this. Another way to interpret this, which I find most, or maybe even, I don't know whether I find it more intuitive, but I find from a technical perspective easier, is to understand it just as the normalized version of A and B, because as we'll see later, if we have joint distributions, we of course define probabilities for two events to happen, and then if we are looking at probabilities of events conditional on another on an event of the complementary random variable, then in this case, then this is just the probability for A and B to occur, but normalized, so that is a probability measure over all the events that can happen in conjunction with B. So it's a normalized, so what I want to say is that the definition, maybe this is also on the slide here, defining the joint probability of A and B, this already defines the conditional probability of A given B. Yeah. So if you say A and B, the probability for A and B is 40, then the conditional probability for, let's say 0.4, I mean, then the conditional and the again, if you define that the probability of A and the probability of A and B, let's say, is 0.2, and the probability of C and B is 0.1, then the conditional probability of A is, of course, given B is, of course, larger than the conditional probability of C given B, because the probability that A and B happen is larger than the probability of that C and B happen. So the magic in defining defining conditional probabilities is in defining joint probabilities. Yeah, this is what we've already seen. One thing that is intuitively clear, but is nevertheless, or is immediately clear, but is nevertheless always sometimes a reason for confusion, is that the probability of A given B is, of course, something different than the probability of B given A. Why should it be the same? But if you think of A being the event that you die, and B that being hung, so the probability to die if you are executed is, of course, something completely different from the probability of hanging, so being executed if you're dead. It's a funny example, but or more or less funny, but so one should not, there's no good reason for confusing this. I mean, just if you look at the formula, these are different formulas, so why should you confuse them? But apparently people sometimes confuse them. And this is what I also mentioned. One can extend this to null events B, but this is technically more challenging, and we don't do that. Again, this is talking about events and not conditional probabilities in terms of random variables. This is what we will see later. Now, coming back to the fact that how conditional probability and independence go together. So if A and B are independent events, then we have the fact that the probability of A and B factors in the probability of A times the probability of B, and by the definition of conditional probability would then divide this by B and, of course, get PA. So given independence, the knowledge of B, so the knowledge that B occurs, does not change the probability of A. And I think this kind of makes this factorization idea of independence quite clear. So if you ask what is the probability of an event A to happen, that given event B happens, and if this probability is in no way affected by the fact that B happened, and then of course B somehow doesn't influence A. But so in this probabilistic framework. So if you observe the probability, I don't know, let's do a COVID example. Maybe let's do it like this. So let's say for each month you measure the probability for a person among 100 persons to get COVID, and you do that for 12 months, and then you do see a probability, or your estimate of the probability is 10%, and then in 1 month, November, you induce lockdown light, and the probability is still 10%, so the conditional probability of people being infected given that there is a lockdown is the same as given that there's no lockdown. Given the event lockdown light, if this conditional probability corresponds to the base probability of A occurring averaged over all possible other events, then of course the lockdown light does not affect the occurrence of COVID infections much. So I think this is a useful thing to think about, and then this just restates the definition of conditional probability, that you can define joint probabilities by means of marginal probability, so P given B times the conditional probability of A given B, or the other way around. And this is something that we will see when we talk about Bayesian statistics, so probabilistic models, because that's the typical way how Bayesian models are defined in terms of a prior and a likelihood. But again, this is nothing but a rewriting of the definition of conditional probability. And again, the crucial thing, and this is what I try to emphasize here, the crucial thing to define a conditional probability is to define the joint probability of A and B to happen. Good. Yeah, this is the law of total probability. It relates a little bit to what I just said regarding lockdown. So the marginal probability of PB can be written as the sum of all conditional probabilities of B given all possible events which are mutually exclusive. So again, lockdown versus no lockdown. Then by multiplying those and then summing, so if you're familiar with Bayesian statistics, this is of course just writing down the joint distribution and then marginalizing, you get the marginal probability of B. And given the time, I think I will not go over that. Because we still want to do this. Yeah, so have a look at this. It's if you are familiar with Bayesian statistics, there's really nothing of much interest in here, because it's just forming joint probabilities and marginalizing. But here's a kind of a formal proof, and the intuitive idea is that the total probability of B can be seen as a weighted average of the conditional probabilities of B. That's fine, but what I think I want to then still go over is, of course, Bayes' theorem, which is a way to compute conditional probabilities. So let A to 1k be a partition of omega with the probability of AI being larger than 0. Then if the probability of B is larger than 0, then for each I to k, the probability of AI given B can be written as the probability of B given AI times the probability of AI divided by the probability of B, which is here with the law of probability of total probability expressed as the sum of the multiples of PAI times PB given AI. And this Bayes theorem is of course just a means to compute conditional probabilities. And how does it come about? So the probability of AI given B is of course defined as the joint probability of AI and B divided by PB. Now we've seen that we can write a joint probability as the product of a marginal probability PAI, or total probability, and that's the same thing, times the conditional probability of B given AI. So this is what we saw here, which is also just a rewriting of the conditional probability definition. And then we already have Bayes' theorem. If you are familiar with Bayesian statistics, you would here call this prior, call this likelihood, and call this evidence. And then we can rewrite the marginal probability or total probability of B as this sum over the other way around of defining the joint probability. So that's just Bayes' theorem. Of course, this is here now written for a finite scenario and so on. We will later see this again, of course, for random variables, and then see this also for continuous cases, also open continuous cases. But of course, it's a little bit easier to show and prove and so on. This is all from the de Groot if you are in a finite case. One thing, of course, to note always is that there's nothing Bayesian about Bayes' theorem. So Bayes' theorem is not necessarily associated with a Bayesian interpretation of probability. It's also a frequent. Of course, you can also have conditional probabilities in a frequentist setting, and then Bayes' theorem applies in the same way. So there's no. It does not mean if you apply Bayes' theorem that you interpret probabilities in terms of uncertainty. So this should not be confused. It's just a tool to compute conditional probabilities, and of course in Bayesian statistics is kind of the most fundamental thing. yeah, that's what I already said. Marginal probabilities are often called priors, and conditional probabilities are then called posteriors. And this is also what I said, PAI sometimes called likelihood and PB evidence. We will see this again when we talk about Bayesian statistics, and then these events will be formulated in terms of random variables. Good. So maybe let me briefly show you then what the plan for the exercises is. So first, in the exercises there are a lot of study questions, not a lot, there will be 10 always, and these are basically things to memorize and learn and immerse yourself in, and they focus on basically most of the things that we have seen. And then in the exercises, there's also a typo, we will see more examples for probability spaces, namely tossing a coin, throwing 2 dice, and tossing a fair coin twice. So we will see 3 more examples for probability spaces, and so this is what we will see later. And in the programming exercises we will see some simulations of probability spaces. Good. So now is a good time for questions. So any questions regarding the last hour? Apparently there are no questions. So again, these are very basic aspects, very basic definitions that you will see in any probability theory and statistics introductions book, and we need them to build upon them, specifically when we then talk about random variables, because our typical probabilistic models are of course not formulated in terms of elementary outcome sets, but in terms of random variables. But to define, for example, what the conditional probability of a random variable to take on a value given that another random variable takes on another value is, we can of course relate this back to the definition of conditional probabilities with respect to events. So we need this as our kind of starting point. Okay, then I suggest that we stop here for this lecture, and maybe then for the data science students, I don't know whether the program is still going on, but you have some time now to absorb this, and then meet again at 1 a.m. to see more examples of probability spaces. And for all the statistical methods people, we will continue in 20 minutes. And for those in data science maybe who would like to revise also very basic mathematical concepts like sets, sums, functions, calculus, matrices, and so on, the first weeks in this other course actually do that, so that may also be helpful. Good, so that was then the lecture, Statistics for Data Science, Probability Spaces for today, and see you again at 1 p.m. Anyway, good. Yeah, then exercises, and like I said, 6 exercises, 3 theoretical, 3 practical, and the theoretical exercises today concerned with other examples for probability space models, namely developing the probability space model of tossing a coin. That's what I will do first. Then Fiore will present on how to develop a probability model of throwing 2 dice, and then I will look at a probabilities model of tossing a fair coin twice, and specific events there and independence. So as you will have also noticed, all these theoretical exercises come with the solution enclosed, if you want, or so the theoretical exercises are not something where I want you to kind of, I mean, in a way yes, but also in a way no. Fiddle around and then maybe find a good solution or not. But I want you to be able to read mathematical text and be able to clarify for yourself what these things mean and then talk about it. So that's the aim of the exercises here. If that's not of your standard because you're used to a higher standard, well, that's fine. But for those of you who are not familiar with mathematical exercises, that's maybe a little bit easier. But I mean, there's still, I mean, you still you need to understand what you're reading and you need to be able to talk about it. So there's still a lot of clarification and understanding and learning involved. Okay, then let me first present the first theoretical exercise to develop a probability space model of tossing a coin. That's relatively straightforward. I mean, it's just another example for a probability space model, as we have seen this morning when considering throwing a dice. Of course, now we have another elementary outcome set. The typical elementary outcome set that is then chosen is that of H standing for heads and T standing for tails, so the both sides of a coin, usually in English referred to as heads and tails. Kopf oder Zahl in German. But again, this is a modeling choice, and if you choose this outcome set HT, then of course if you write down your sigma algebra, for example the power set of that, you will have everywhere H and T's. You can of course encode heads and tails also with 0 and 1s. So, and if you for example think of modeling a fair coin by a Bernoulli distribution, as we will see later, has as its outcomes values 0s and 1, and if you use this as a model for a fair coin, then in a way you always need to map the 0 and the 1 to heads and tails respectively. So again, it's a modeling choice how you set your outcome set, but of course it's reasonable for a coin which has two sides and for which you don't think it will land on its margin and stand up. Often reasonable to choose two elementary outcomes and then call them heads and tails, H and T, or 0 and 1. Then for probability space, you of course also need a sigma algebra, and as always in these finite outcome sets, the power set is readily available, and hence is always guaranteed to be a sigma algebra. So why not choose it? So let's choose the power set, and then of course we have the set of all subsets of H and T, and they are listed here. So the empty set is always in the power set. Always a subset of a set. The complete or the outcome set itself is a subset, and then okay, there are only two elements in there, so the other subsets are H and T, and of course these subsets again can or assume some meaning in the model of a fair coin, namely that neither heads or tails occurs would be the empty set, that heads occurs would be the set H, the tails occurs would be the set T, and the event that heads or tails occurs would be the event H T. Yeah, so either, and that's just anything. Heads or tails occurs sounds a little bit weird, but it means that anything happens. So either heads comes up or tails comes up, and of course this is just the full set, and that has the probability 1, because with probability 1 either heads or tails occurs in this model. Again, if the coin is lost or lands on its side and stands up, then the model is not a good model. And I think it was about tossing a coin, so it doesn't say anything about a fair coin, but again, like we discussed this morning, and here with the same, because it is a copy and paste thing, with the same typo as this morning. Sorry for that, I didn't know that this came up again. We can specify the probability for all elementary outcomes, in this case for the H and the T, and then we can compute probabilities for all remaining sets by means of the sigma additivity. That's a little bit overkill in this case, actually, if you think about it, because the only thing that corresponds to union here would be HT, and by definition of the probability space, the probability assigned to the set HT is already 1, so that's a little bit overkill. But nevertheless, that's the logic here, and what I'm trying to do in this example is to show you that it's a recipe. So you don't actually, if you write down these probability space models, you shouldn't maybe even not think that much. You should follow the recipe of you need an outcome space, you need to find a sigma algebra, and finally you need to specify a probability measure. So sorry for this typo again. Oops, this is somehow a little bit sensitive. And then if you specify the probabilities for all the elementary outcomes, then of course if you use a fair coin, then you would say that probability for heads is the same as for tails, which then leads you to a probability of 1/2 for each of them, because it needs, if you look at the union, it needs to sum. But of course there is no need for heads or tails to have the same probability. If you think your coin is biased, then you might model a biased coin and see how your model makes predictions in the case of bias. So again, what I'm trying to emphasize here is that you need to specify the outcome set. Then based on the outcome set, which is either infinite, then you can map it onto the real numbers, and then you can use the Boole sigma algebra, or let's say uncountable, and then you can map it to the real numbers. Or you have a discrete finite set, then you can use the power set, and that's essentially all you need. And in all these examples, that they are these kind of real world examples of coins and so on, and dice and so on, it's usually that you're in the discrete case, but then it's a modeling choice of how you assign the probabilities. Good, and that would be then, of course, a very basic probability space model. So the task is to develop a probability space model of throwing 2 dice and nothing else. So the question is, of course, first, what are the elementary outcomes, or what is a reasonable elementary outcome set? And if you throw 2 dice, you have, of course, let's say a red and a blue dice, and then and you throw them simultaneously, you always have one showing up a certain number of pips and the other one showing up another number of pips. So it makes sense to consider the set of ordered tuples D1 and D2, because we think that this is something one can debate, but here it's of course assumed that we can distinguish the 2 dice, and each one takes on values in 1, 2, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And then the cardinality of this space omega is 36. So far, I think we agree, and this is also what you did. Where things went a little bit weird in your presentation is that you then talked about the event sets, so the sigma algebra, and there you essentially only considered the cardinality, or let's say you wrote the power set as 2 to the power of omega, which one can do, but actually I introduced some notation for the power set earlier, so please use this. And then it's correct that the cardinality of the power set is 2 to the power of 36, but the question is more what is actually the sigma algebra, if you and what are the elements of the sigma algebra if you formulate the probability space. And there, of course, these are now really, really many, so you could write them all out. I mean, then you would have a lot to do, but here I selected 3 examples, which in a way show interesting things. One of them is something that you had in mind, so that the sum of pips equals something. That's definitely an event of interest, but that's just one of the many events that one can look at. So sum of pips equals 4 would have as elementary outcomes 1, 3, 3, 1, and 2, 2. But of course, another event would be that 3 pips show on the first row, so on the first dice, and that would be the pairs 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, or that you have a push or doubles, so that would be the elementary outcomes 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. And of course there are many more, so in principle you could one could extend this list by many events. And then the probability measure that one needs to define for a fair dice would be, and I think you also got this correct, or sensible, let's say, not correct, because that's always a little bit weird, because it's a modeling choice. You would assign, because you have 36 possibilities or 36 elementary outcomes. Of course, if you think both dice are fair, or your thing that you play those, so your double dice is fair, then assigning 1 over 36 for all outcomes in the outcome space being 1 over 36, that's fine. And then again, you can for all other events, and not only for these events where the sum equals something, you can evaluate probabilities. So for example, I'm of course I'm doing this here again also for where I'm using the sum, but let's for fun, let's do it for something else, namely for the case that we have a push. So for the case of doubles, one can, based on the sigma additivity, now evaluate the probability of a push, and because there are 6 events in the elementary outcomes set that correspond to a push, our set A3, we would have 6 over 36 for this event that we have a push. So I think what happened a little bit in your presentation is that you conflated this idea of evaluating the sum of pips with the formulation of a probability space model. Probability space model just defines the omega, the sigma algebra, and the probability, and that's that. If you then do something else, for example, I mean, you can say, okay, I want to look at all probabilities for the event that the sum equals 1, or the event the sum equals 2, or so on. You can do that. You can also address this with random variables. But there's more, right? So and you shouldn't forget this, and make sure that this is clear, because the definition of the probability space model it just entails specifying omega, the sigma algebra, and the probability measure, and that's it. Good. So that was that exercise. Are there questions by other people, not Fia, or other people regarding this exercise? That doesn't seem to be the case. Now, the last exercise that I put up here, and that could have been presented, but was not, because people chose to not do that, is the probability space model of tossing a fair coin twice. And that's the first thing. So developing this model, and then this exercise is actually about independence, and finding that that a set of 3 events can be pairwise independent, but not completely independent. And this follows this example in de Groot and Schelvisch. And let me show you what this is about. So as we will, as we in a way saw here, and also we'll maybe again see later if we consider sums of two dice and so on. There are two ways to address these things of doing a very simple probability thing twice. So one formal way that we discussed last year, but that was not a great success, was to consider product probability spaces. So if one has independent independent probability spaces, then one can use them to model these kind of multi outcomes. Another way to do it, and that's the way that we just did it for the dice and are now doing it for 2 coins, is to consider the double things that we are or triple or whatever things that we are modeling directly as elementary outcomes, and that's the case here. So we are considering throwing a fair coin twice. So the elementary outcomes that we can observe are of course heads twice, so HH, heads first, and then tails, so HT, tails first and then heads, so TH, and tails twice. So these are elementary outcomes. And again, we can define, because this is of course still a discrete and finite outcome set, it's reasonable to take the power set as the sigma algebra, which then contains all possible events. Let me see. No, I don't have any examples here, but of course you can think, so here you can actually write out the whole power set still, I guess. So it has 16 elements, so 16 to the power of 4, 2 times 2 is 4, 16 elements. So you can write it out and give your own interpretations of what the events mean. If we then, to finish the formulation of the probability space model, we can again, because we have a discrete probability space with a discrete and finite outcome set, we can again just assign probabilities to the elementary outcomes and use sigma additivity to then evaluate the probability of all other events in the sigma algebra or the event set. And of course, and this is then where one needs a little bit maybe even of intuition already, is a sensible thing to do is to assume that all the elementary outcomes have the same probability, which of course you can motivate by the fact that on each trial you start with a probability of 1/2, and then if you have independence you get the probability of heads 1/2 times the probability of heads 1/2. But of course this is not formalized here. This is more kind of an intuition behind that, and what the definition says, the definition just says to each of these elementary outcomes, HH, HT, TH, and TT, we assign a probability of 1/4, and we don't discuss where this is coming from. It's just a definition, and that's something that you can of course do in math. You can define things however you like. You might need to justify to other humans why you chose these definitions, but in the end you can define whatever you like. Now, based on these definitions, so again, formulating a probability space model means defining the elementary outcome set omega, defining a sigma algebra on it for discrete finite, usually the power set, and then defining the probability measure for discrete finite things is enough to specify that for each elementary outcome. Now we in the exercise was not only to formulate this, but then consider 3 events of interest, and these events of interest where heads appear on first toss, heads appear on second toss, and both tosses have the same outcome, which is a nice typo. Sorry for that. I also failed because I have too many typos here. This should be TT. TT. So heads appears on first toss. H, the heads appears on the first toss. HT, heads appears on the first toss. the question is, what's the probability of that? Well, that's the probability of the union of HH and HT, which by sigma additivity we can then write as the sum of the probabilities, and each one of them has 1 over 4, so that's 1/2. Heads appear on second toss. That's HH and TH. So note the difference here. So here HT, here TH, but otherwise the calculation is of course the same. Again, it's 1 over 4 for each of the events HH and TH, and both tosses have the same outcome. Of course, is the event HH and the event. Let's see whether that. Oops, no, that was fine. What I want is, yeah, that should be TT, and then also here this should be, does that do something? No. This should be TT, and this should be TT. Can I draw it? Oh, let's not try that now. So this all should be TT. But of course, the logic is again the same. Each of these events HH and TT has a probability of 1 over 4. They are mutually exclusive or disjoint, and hence we can evaluate the probability of this event again by summing and get 1/2. And then the question was to show the pairwise independence of these events, and pairwise independence means that you consider two events and you show that the intersection of these events has probability corresponding to the product of the individual events. So let me briefly for this go back to the definition of independence that we discussed this morning. So two events A and B are independent if the probability assigned to the intersection of A and B corresponds to the product of the probability of A times the probability of B. And if this holds for two events, then they are pairwise independent. So let's have a look here. Of course, we first need to check it's correct actually. We first need to check what is actually the intersection. So we have A1 and A2, which was again heads first versus heads second. So we have the intersection of the events HH, HT and HH, TH. And of course, the only elementary outcome that is in both is HH. So the probability that is assigned to the intersection of event A and event A1 and event A2 is the probability that is assigned to HH, and this we know it's an elementary outcome for a fair coin. This is the probability of 1 over 4, and of course 1 over 4 is the same as the probability that is assigned to the event A1 times the probability that is assigned to the event A2 as we previously calculated, namely on this slide. So that we calculated that P A1 is 1/2 and P A2 is 1/2. So we found that the probability of the intersection of these two events is the same as the product of the probabilities of the individual events. And so to check that next, we check it for so to show the pairwise independence, we need to consider all possibilities. So A1 and A2, A1 and A3, and A2 and A3. And if we look at A1 and A3 first, then we have HH, HT, and here now correctly specified the event A3, namely HH and TT. Again, the only element in the intersection is HH, and then exactly the same logic holds as previously. So just if you are happy with this, this is exactly the same, with the only difference that this event here has changed. And finally A2 and A3, and this is also fine here, so heads second, and the intersection with the event that both outcomes are the same. Again, that's HH, and again we get the probability for the intersection to be the same as the probabilities multiplied for each event. So they are pairwise independent, and now the thing is that in this example, however, while these three events are pairwise independent, these three events are not independent, because for them to be independent, this needs to hold for all for arbitrary subsets of the event index set, and one of these arbitrary subsets is of course having all three in there. And what we're looking at here is the probability of the intersection of all three events. Next typo. This will be fun. Maybe I should. The good thing is in your batch the typos of the first year out, but now you have the second year typos. There's a double typo here. What's going on? Two. So we are looking at the intersection of A1, A2, and A3. Again, A1 was HHHT, then we have A2, HHTH, and A3 was HHTT. The intersection, the only element that is in all three of them is HH. So the probability of the intersection of A1, A2, and A3 is the probability of HH, and that's 1 over 4. But that is not the same as the product of all the individual probabilities, which is 1/2 times 1/2 times 1/2, which is 1 over 8. So these three events, although they are all pairwise independent, they are not independent in the sense of the definition of independence, namely that independence needs to hold for all arbitrary subsets of the index set of these events. So again, what I'm referring to here, if this didn't get quite clear, is this thing here, the intersection over an arbitrary j, which is subset of equal to, would be actually more correct. So we can improve. So we're getting all the typos. If you don't find them, I find them. For an arbitrary index set, the intersection needs to again factor into the product of the probabilities, and this again for this in this exercise is not fulfilled, because if you look at the intersection of all three events, then you find that the probability of the intersection of all three events is different from the product of the probabilities of the individual events, because 1 over 4 is not the same as 1 over 8. Good. So that was a little bit more than going beyond just formulating a probability space model, but also looking at the notion of independence of events. It's a little exercise. One gets a little bit used to what these formulas are supposed to mean. One can introduce arbitrary typos. Yeah. Any questions regarding theoretical exercise 3? Or any other typos that I didn't catch? Okay, that does not seem to be the case right now. Then I suggest we have another break. So we have like almost 45 minutes now. So let's have a break until 2, and then after 2 or from 2 onwards, look at the programming exercises, which are actually concerned with simulating these basic probability space models and looking at specific event probabilities that then result. Okay, but let's first have a break. Hopefully corrected all the typos, or the, let's say, 3 typos that were in the exercises by now. If you find more, send me emails and I will correct them. Okay, doesn't seem to be the case. Thank you very much. That was also very good, very clear. Yeah, and as you said in the beginning, or I think you said it, maybe also Veronica said it, these exercises are not meant to be hard, maybe especially these first exercises when we are now looking at probability spaces, they are also a little bit boring, let's say, if you're interested in data science, but we will get to exercises that are much more related to kind of data science and finding maximum likelihood estimates or deriving Bayesian posteriors and so on. But I think it's very important that also in these simple exercises one works like you did and Veronica did, very step by step, in a kind of relaxed fashion, no panic, and just clarifies the things. So that was very good. Good. Thank you, both of you, then. And let me then finally discuss the last exercise, which is actually the second exercise. Okay. I think actually Veronica did this already. She maybe it was in the original formulation of this. This was in there. Then I don't actually have to say that. Actually, I was a little bit confused when Veronica presented that, but then I thought it's maybe part of the first exercise, but it's fine. Don't worry, everything is fine. So this was about 2 events that are not independent, and the idea was that's exactly what Veronica already did, so I don't have to do that again, or is it? Confuse myself here. That's okay. Yeah. In any case, I also did this exercise, but I didn't do it nicely in a Jupyter notebooks that I converted to a presentation, but I just did in Spider. But now that I know this presentation thing might be interesting, but I think this is exactly what Veronica already showed us. So I'm considering here 2 non-independent events, which are 2 events with positive probability, which are mutually exclusive. So disjoint events with positive probability for dice. So 1, 3, 5, 2, 4, 6. And then I know that you guys like to put into the number of samples directly into the random sampler. I often actually write a for loop for that, for the main reason that if things become more complex, it's sometimes helpful to go step by step. So for example, if you transform realizations, then for me it's conceptually simpler if I transform after sampling each one, but of course it's computationally less efficient, but of course that's not really an issue here. So I go over all the samples, uniformly distributed over 1 to 6, and then I use this Python in check whether what I observed here, so the pips, is in this event, if in this event, or in it's in both events, and count how often they are, and then I report the normalized frequency, and because they are mutually exclusive, I think there's something, they are non-independent, but a little bit confused with respect to Veronica's example, but maybe Veronica can comment on that. But the probability that none that they occur together is 0, and then the probability that A given B occurs is also 0. So that was my example. It's a little bit, I think it's a little bit lamer than Veronica's, because I end up with this, or I have these mutually exclusive events that never happen together, and yeah.